Hi, welcome to my YouTube channel Vaishnav 360. Like, share, subscribe, and do not forget to hit the bell icon.
Today we are going to do the introduction to exercise 1b. So, in the starting of the introduction of exercise 1b in functions, we should know what is inverse functions. What is inverse functions? Okay, inverse functions. Now, starting with inverse functions, we'll write if f maps a to b is a bijection, then the relation f inverse is equals to b a, pair b a, and pair a comma b belongs to f, okay, is a function from b to a. What it is? B to a. In normal functions it is a to b, but here it is b to a. That's why it is known as inverse functions and is called inverse of f. We'll take example. Okay. Example is a and b pair is there. We'll take 1 2 3 in domain and xy in codomain. Now there should not be any element remaining in domain, but it could be in codomain. So this is normally not a function. So how can it be an inverse function? That's why it is not a inverse function. Okay. Now another a and b, two pairs, 1 2 3 xy. We can take two images here like this. Okay, these two are remaining, so again it is not a function. A and b again a pair. Okay, in this pair 1 2 3 x and y again, these two here and one here. One codomain can have two images. Here another point is there. One domain has two codomains. It is also wrong. That's why this is not a function. There are 2 points to say that this is not a function. That is, first one, the domain has two codomain elements, and another one, in domain 2 elements are remaining. That's why it is not a function. For this, it is not like that. 1 and 2 are domains, but there is only one codomain as an image for 1 and 2, so it is a correct one. And the next one is the uh, is not remaining in this one. It was remaining. Okay, in this one also 3 was remaining, but here 3 is not remaining. Instead of 3 remaining, y has taken the place of image for 3. Okay, now this is an correct inverse function. We can write this in two ways, either b to a or a to b. Okay, now a and b 1 2 3 x y z. This is an injection and surjection. We can take it as both step by step, one to one or step by step function, can we can say this, and on to function, because what is codomain is equals to range. XYZ is codomain. Range equals to XYZ only, right? So it is a surjection and injection, because for each codomain we have a domain as an image. So it is injection, that is one to one, and surjection, that is onto. Both are existing. So it is therefore a bijection. Okay. Now we have learnt what is inverse function. Okay. I have told you this one before now. AB 1 2 3 XYZ, step by step. First one here image, second here image, third here image. One by one. Okay. The next one is surjection, as this is codomain and the range is also same. That's why we can consider it is a surjection also. So totally, if these both are present in one function, then we can call it as bijection. So these are the examples. Now we will do composite function. Okay, we are going to do composite functions. Now we are going to do composite functions. Okay, composite function. We will write the definition for it. If f maps a to b, g maps b to c, then the relation a comma g of f of a and a belongs to capital A is called composite of G with F, and is denoted as GOF. Okay, composite functions is nothing but if F maps A to B and G maps B to C, then the relation of these both F and G can be written as G of F, and this is called as composite of G with F. Okay, now we will take some examples to understand it clear. Examples. Okay. uh, okay, A B C. All right, 1 2 3 in A set, A B C in B set, and XY in C set. First we'll do A and B. Okay, it is step by step, that is one by one. Okay, that is an injection. We can write it as like this, and now B to C. B to C is like this one, and one codomain can have two images. So like this. What is this A and B? A and B here represents F. B and C represents G. A and B is F. B and C is G. Okay. Now What is f of 1? F of 1 is nothing but a. What is f of 2? F of 2 is b. Okay. F of 3. F of 3 is c. Huh? Now we'll find out for g. What is g of a? G of a is x. G of b. G of b is y. G of c. G of c is also y. Okay. Now we have got normally what we get an answer, but we want we have a composite function, right? We should get a answer of a composite function. So now for a composite function, the answer should be in the form of GOF, right? Now we'll find out GOF of 1. G of GOF of 1 is x. How? GOF of 1 here and C here, x. G here, right? F. GF1. Here G, this one first row. At the end, what is the answer? X. So for 1, GOF of 1 is equals to x. Alright. Now we will find out GOF of 2. What is it? GOF of 2, second row. Last answer is y. So answer is y. Okay. I think you all may understand. Now GOF of 3. What is it? Third row. It is connected like this, right? We should miss out this b bit and directly write the answer what is here. So what is it? Y again. So we have completed what is an composite function now. This is an example for a composite function. Now it is nothing but we should write the end answer if we have got g of f. If we get g of f or anything, we should directly write the end answer. We should not write the first answer in the middle set, and then again we should write the last answer in the last set. Okay, we should directly write from the first set to the last set. Okay, now we are going to do the next one, that is our theorems which are required for our exercise 1b. Okay, now we are going to do the theorems. Okay, first of all, we should know all the theorems to do the problems in exercise 1b. So hear carefully and learn these theorems so that you can do more problems. Okay, if you do more problems, it is benefit for you only in exams, that you may do fastly and you will have time to check the paper. Okay, now what is the first theorem? First theorem is, let f maps a to b comma g maps b to c. So we can tell it is an inverse. No, it is an, what we can say, yeah, we have learned now only, no, f maps a to b and b to c maps d. Okay, now we can say this as a composite function, because now only we have discussed a to b and b to a. For this, a composite function answer will be directly from a to c, right? I think you got it. Now it will be a bijection. Okay, bijection. We are thinking or assuming that it will be a bijection. Okay, now it is a bijection, right? Now then go f maps a directly to c is a bijection. Now F maps A to C is also a bijection. We are thinking that F maps C is also a bijection. That is the composite function answer. Okay. Now let us prove and solve this one. Solve. Okay. Let us prove that G of GOF, by mistakenly I read it as G of GOF maps A to C is a injection. We have given, we have got in the question the given, that is F maps A to B and G maps B to C are injection functions. Injection functions, right? Now let us consider A1, A2 belongs to A. Then GOF of A1 is equals to GOF of A2. Since injection of G, since it is injection of G, G of F of A1 is equals to G of F of A2. Now we can write this GOF as this. You may think how it is possible, but now I will talk to you about the previous problem which we have done. I will show you that and I will tell you how it is possible. Now here G of F means nothing but 1 to A and A to X, right? Now here G of F, let us take 1. Okay. Now we can write this as G of F of 1. What is F of 1? F of 1 is A. What is G of A? G of A, G of A is X. What we have got the answer here? GOF of 1 is equals to X. GOF of 1 is equals to X. So we can write GOF of 1 as G of F of 1, right? Now we'll get back to the problem which we are currently doing. Okay, I think you may understand and we'll continue now. So here we have got G and G will cancel here as it is same. If we transfer here it will get divided and again it will get cancelled. So now here again F of, if this F goes here it will get cancelled. So we can directly write A1 is equals to A2. Okay, A1 is equals to A2, right? Now this we can tell it as an injection, because in normal injection means x1 is equals to x2, right? Now here we have changed the variable to A, so we can write it as x1 is equals to x2 or A1 is equals to A2 or any other variable or alphabetical letter. Now we will do the surjection part. Let us do the surjection part. So let us prove that G of F maps A to C is a surjection. I have learnt it as G of F, but for you it will be confusing. So you should read it as GOF. Okay. Maps A to C. Now we should do the surjection part, right? Let us consider that A belongs to capital A, comma B belongs to capital B, and C belongs to capital C. Okay. Now in the question we have got F maps A to B is a surjection. The surjection, that is F of A is equals to B. Now G maps B to C is a surjection, that is G of B is equals to C. I will write here in the diagrammatical form so that you can understand. A, B and C. Here A, B, C. I think it will be tidy, but I will explain. No, you will understand. Here one arrow mark. This is an this image is this, and this image is for this. Okay, one. Sorry. Here F and here G. So we can write like this. Okay. Now C is equals to G of B, and G of B is equals to G of F of A, and it is totally called GOF of A. Now therefore GOF GOF of A is equals to C. Okay. Now GOF maps A to C is a surjection. Okay, it is an surjection. So totally, therefore GOF maps A to C is a bijection. Okay, I think you understood the first theorem. Now we'll go to the second theorem. Now we are going to do theorem 2. Theorem 2. Okay, so to do theorem 2 we should write, let F maps A to B, comma G maps B to C. From now we will get every problem G of F or F of G anything, or F inverse of G, F inverse of G inverse, and G inverse of F inverse. Okay, like that we will get. Okay. Now let F maps A to B and G maps B to C be bijections. Bijections mean what? Something which have both the conditions, that is injection and surjection, then it is called as a bijection. Okay, bijections. Then GOF total inverse is equals to F inverse of G inverse. Proof. Now we should do the proof. Okay. Now in proof, given is F maps A to B and G maps B to C are bijections. Okay. Now G of F maps A directly to C is also a bijection. We got this from the last theorem, that is theorem 1, bijection, right? Till here it is okay. But what is F inverse? F inverse or G of F total inverse, that is C to A, is also an injection. In multiplication, 1 into 0 is 0 and 0 into 0 is also 0, no? That is 0 into 1 is also 0, 1 into 0 is also 0, no? So here also like that only, they are bijections. A into C are same, C into A are same. That's why we can write it as A to C and C to A. F inverse maps B to A. From here we can conclude that F inverse means B to A and G inverse means C to B are bijections. Simple. If F and G are bijections, F inverse and G inverse also should be a bijections. No, that's why we got F inverse and G inverse as bijections. Okay. Now F inverse of G inverse maps C to A is also a bijection. No. Okay. And therefore G inverse maps C to B, no, and F inverse maps B to A. For this, I have written separate. Written separately. I have written separately. Sorry. For this statement, I have written here, and for this statement, I have written here separately. Okay. Now here G of F whole inverse and F inverse of G inverse are defined on on same domain. Okay. Now let let A belongs to capital A and B belongs to capital B. C belongs to capital C. Then F maps A to B is F of A is equals to B and F inverse is B to A. Okay, I think you may see it clearly now. Now we'll do same for G maps G of B. For G of B, we should do G maps B to C is equals to G of B is equals to C. That implies G inverse of C is equals to B. Okay. I think you all are getting clearly what I am writing here. Here, by writing the statement only, you can understand how it changed and why did this answer came. That's why I'm specifically not defining it like this uh, or something. This is like this and how it came. I am not explaining like that because we can by seeing only we can understand how it came. So for C, G of B is equals to G of F of A is equals to G O F of A. Okay. Now C is equals to G O F of A, no? Now we can write it as GOF of inverse C is equals to A. This is first one. Okay, this is first equation. Okay, now we will do this second equation. How it will come second equation, I will show you. To get the second equation, we should find out F inverse O G inverse of C is equals to F inverse of G inverse C, right? Now F inverse B is equals to A. Okay, now F inverse O G inverse of C is equals to A is the second point or the second equation. Okay, I think now you can see. Yeah, now you can see clear. All right, now therefore we will get from equation 1 and 2, that is first equation A. Here in first equation we got GOF whole inverse C is equals to A, and F inverse O G inverse of C is equals to A. Here A only, here A only. So we can write that GOF whole inverse of C is equals to F inverse O inverse G inverse, sorry, O G inverse of C is the answer. Okay, we will get the proof, the answer. In the question, what is given here? You may say this. What is given here? GOF whole inverse is equal to F inverse of G inverse. Right. Now, what is the answer here we got? Here also same only, no? So, the proof here we did is correct. Now, we'll go for the third theorem. Okay. Now, we are going to start the third theorem, that is, let F maps A to B, that is I means identical function. No, we have done in the starting identical function, that is A of A, and identical function of B identity function. This is the symbol for identity function. Okay, this is the symbol for the identity function. If in exam there will not be any sentence in which this is an identical function or etc., by seeing this symbol we should recognize it that it is a identity function. Okay, now identity function on A and B respectively, okay, respectively. Now then F of IA is equals to F, wait, F of IA is equals to uh, F of IB is equals to F. Okay, now we should prove that it is an identity function with using F of IA is equals to F or F of IB is equals to F. Okay, now we are going to do the proof for this. Proof. Now proof. We are going to do the proof now. Check it out. Yeah, we should write the given first. What is given? Given is IA maps A to A and F maps A to B. Here if OIA is a function from A to B. I think you may see it clearly. Okay. Now here FOIA is a function from A to B. Alright. Now F maps A to B. F maps A to B, no. Now what does FOIA maps? It is nothing but A to B only. Here F and FOIA have same domain, that is A. So here they are same. Okay. Now let A belongs to capital A, comma F of IA of A is equals to F of IA of A. Now F of A. Okay. Now it is totally F of IA is equals to F. This is the first equation. This is the first equation. This is A belongs to capital A. Okay. Now given here we should know what is the second equation to do the proof. So we should find the second equation. To find the second equation we should do this. IB maps B to B and F maps A to B. So F maps A to B, comma IB maps, sorry here, IB maps B to B. I am writing here 2 times so that I can write the concluding statement here. Therefore, IBOF is a function of F and it is from A to B. Or you can write directly of IBOF is a function from A to B. You can write this directly. It is long, it may be long. To be short, from A to B is okay. Now, the another concluding statement is therefore IBOF is a domain A and F is also of domain A. Consider A belongs to capital A and B belongs to capital B. I think you can see this. I am worrying for this because in my every video I got few letters coming like this down and I am writing on here. So that's why I am going to do or again or see twice or thrice before writing the next line. Okay. Now I think it is clear. Now we'll consider To consider, we should take it up, or else again the same mistake will appear again, as we have did in the before video. Now, to consider A belongs to capital A and B belongs to capital B. Hi Rappa, how long is this paper? Now it ended. Now, to consider A belongs to capital A and B belongs to capital B, IB OF of A is equals to IB F of A. Okay, it is F maps A to B, right? Then F of A is what? It is B. So IB of B it is. Now is equals to B. Since IB is a identity function. One you can take. Now IBOF of A is equals to B. This is the first equation, right? Now actually we have got the second equation, that is F maps A to B, that is F of A is equals to B, the second equation. Okay, from EQ, that is equation 1 and 2, IB of F is equals to F, that is the answer. This is the second equation actually. Here, okay, okay, I think so. Here, this is Roman number first equation, this is Roman number second equation. Here, second equation. Okay, now therefore from Roman number 1 and Roman number 2, FOIA is equals to F is equals to IBOF. I told you, no, in the question we should do the proof. In the proof, what we have got is this. In the question also, we have got the same only, because if F01A is equals to FO1B is equals to F, or it may written like this also, no, like this, and here like this, we can write it like that also. So here we can also write this FO1A, IA is equals to IBOF is equals to F. We can write it anyway. Okay, so this is the answer. We can write this also as an answer. Okay, we will now go towards the next theorem, that is fourth one. Now we will do the fourth theorem. To do the fourth theorem, we will first write what to prove. To prove, what is the question? What we should prove actually is, let F maps A to B be a bijection. There is nothing difference between a problem and a theorem. The theorem is the main, if we say it is a function or anything, it is the main step through which we can do the other problems in textbook. So we will learn it as theorems. Only these are learned or by hearted, and the problems are done by their own. We can say it as a formula for the problems. Okay, the theorems are the formula to do a problem. like that. So let F maps A to B be a bijection, then F O F inverse is equals to IB, that is identity function, and F inverse OF is IA, that is identity function of A, and this is identity function of B. Okay. Now we should prove that F of F inverse is equals to identity function of B, and F inverse of F is equals to identity function of A. We should prove this. To prove this, we should write first the given, that is F maps A to B is a bijection, and F inverse B to A is also a bijection. I think you may see it. And F inverse of F maps A to A is also a bijection, and F of F inverse maps B to B is also a bijection. In the question, they have given in the short form. I am writing in the proof that the given is these all in a extended form, so that because of elaborating you may get it clearly. Now here again given, what we have given means what question is given, that is IB maps B to B and IA maps A to A are also bijections. Okay, here FOF inverse and IB are defined on the same domain B. F inverse OF and IA are defined on the same domain A. Okay. These statements only clarify your doubts, so copy or hear it carefully. Okay. Let A belongs to A, capital A, and belongs to capital B. Okay. F of A means F maps A to B, and F of A is equals to B, that is F inverse B is equals to A. IB of B is equals to B. Okay. F of F inverse B is equals to F of F inverse B is equals to F of A is equals to B. Okay. Now we will do the further solution, that is f of f inverse of b is equals to b. This is the first equation what we get. First equation. And ib of b is equals to b. This is the second equation what we get. Okay. Now consider, before considering we should therefore write f of f inverse is equals to ib. Okay. Now consider f of f inverse of f a of a is equals to f inverse of f of a is equals to f inverse of b is equals to a. Okay. I think you can see clearly now. Okay. Now this is a small a. Okay. This is small a. Now, all right, we have done here all this. Now f inverse of f of a is equals to a. This is the third equation what we get. And ia of a is equals to a. That is the fourth equation what we get. Therefore f of f inverse of f is equals to ia. We have hence proved this. This in question we got here in the question. You may see this. Here we got right this one and this one. I have got answer here C. Here I got one answer, no? This and this tallies, and I have proved the theorem 4. So these are the four main and important theorems which you should know. Now other theorems we have only statements. Those are not much important, but we should need to solve the problem. So I am going to tell them now. Now we are going to do theorem number 5. Let f of f maps A to B and G maps B to C be such that GOF is an injection, then F is an injection. Okay. Oh, sorry. Now it will be clear. Now, okay. Theorem 5 states that F maps A to B and G maps B to C be such that G of F is an injection. That means A directly goes to C and the answer will be C. Now G of F is an injection, that is A to C is an injection, then F is also an injection. Okay. Now we are going to do theorem number 6. Theorem number 6. Theorem 6. Okay. Now in theorem 6, let F maps A to B and G maps B to C be such that GOF is a surjection. A surjection. Here theorem 6 states that F maps A to B and G maps B to C uh, is a surjection if G of F is a surjection. Same as here in theorem 5, if F maps A to B and G maps B to C is injection, then G of F is injection. Here also, if F maps B A to B and G maps B to C, then G of F is also an injection. Sorry, surjection. Okay. Now we are going to do theorem 7. Theorem 7. Theorem 7 states that the identity function function IA maps A to A is a bijection. That is, IA inverse is equals to IA. IA inverse means opposite of IA. That is equals to IA. That is the original one. Then we will do theorem number 8. We should always by heart the theorems through which we can solve the problems easily. Okay. Let In theorem 8 it states that let F maps A to B be a function, then F is a bijection if and only if these exists. This is exists functions G maps B to A such that FOG is equals to IB and GOF is equals to IA, and in this case G is equals to F inverse 1. Here theorem 8 states that F maps A to B should be a function. Then the function F is a bijection if and only if these exist. G maps B to A such that FOG, IB and GOF IA, and in this case G is equals to F inverse. If F is a bijection, this exists that G maps B to A, that is F of G is equals to IB and G of F is equals to IA. Okay. If this is a bijection, then this is the answer for F of G and G of F, and in this case G is equals to F inverse. Then here this G is equals to inverse of F. Okay. Now we'll do theorem 9, which states, wait, first of all I will write the heading. Theorem 9. Okay. In theorem 9 it states that let F maps A to B, comma G maps B to C, and H maps C to D. Here a new variable is added. F, G is common and H is the new one which is added. But we can take it as S, Y, X, Z or anything we can take it. But here I am taking H because F, G, H are continuous. That's why. Then H, O, G, O, F is equals to HOG of OF. That is composite or composition of function is composition of function is associative. If there is uh, three functions, then it is called as composition of functions and they are associative. So we have completed through all the introduction of the exercise 1b. Now in the next video we are going to do the problems in 1b. Thank you for watching.